Welcome to the video lecture on related rates. In many practical applications of calculus, several related quantities vary together. Therefore, the rates at which they vary are also related to each other. The generic related rates problem asks for one rate of change given information about one or more others. So this video lecture is going to be about word problems involving related rates. Now, the idea behind solving related rates problems is the same. Start with an equation relating two or more quantities that vary with time. Differentiate both sides with respect to time using the chain rule. The resulting equation relates the rates at which the quantities vary. Use it to solve for the desired rate. Now, when we do these related rates problems, you are always going to be taking the derivative with respect to time t. So instead of having d over dx, we're going to have d over dt. So in order to do this derivative correctly, you want to make sure that you use that chain rule. Now, we're used to taking the derivative with respect to x. So when you see something like the derivative with respect to x of x squared, if these two variables match, then you get to do your normal derivative. So the derivative of x squared would just be 2x. Now, we've seen in implicit differentiation problems where you take the derivative of y terms with respect to x. So if you have an x here and a y here, to take this derivative, you would take the normal derivative of y squared, which wants to be a 2y, and then you would multiply that by dy dx, or if you prefer, you can use that y prime notation. Now, that's what we're going to do as well in these related rates problems, but instead of having an x in the bottom, we're going to have a t. So very rarely, but occasionally, you might take the derivative of a t term with respect to t. So if these two t's match, then you take your normal derivative and you're done. So derivative of t squared would just be 2t. So this time, if we take the derivative of an x term or a y term with respect to t, so that this variable and this variable do not match, then we're going to need to take our normal derivative of the term, just like we would expect, but then we're going to multiply that by either a dx dt or a dy dt. So for example, the derivative of x squared wants to be a 2x, but this time we're going to multiply that by our derivative, which would be dx over dt. Now, sometimes we get a little bit lazy, if you will, and we just write it d2x times x prime. And you just want to make sure that you recognize that this time the x prime is a dx dt. It's with respect to time. Similarly, if I wanted the derivative of y squared with respect to t, the normal derivative wants to be a 2y, and we would want to either multiply that by dy dt because of that chain rule, or you could just write 2y y prime. But this y prime here represents dy with respect to x versus this y prime, which is dy with respect to t. So in related rates problems, it's always with respect to t. In implicit differentiation problems, it's always with respect to x. Okay? So our procedure for solving related rates problems. Number 1, assign variables to all given quantities and unknown quantities. Make a sketch and label. And having a nice picture is really going to help you be able to do these problems a lot easier. Number 2, write an equation involving the variables whose rates of change are given or are to be determined. Number 3, use the chain rule to differentiate implicitly on both sides with respect to time using what we just talked about above. If you're taking the derivative of any x term, you want to multiply that by a dx dt or an x prime. And if you take the derivative of any y terms, you're going to multiply it by a dy dt or a y prime. Finally, number 4, substitute in all known values and solve for the missing amount. You don't want to substitute in any values until the very last step. Okay, let's take a look at our first example. Here we have a point which follows along the curve y equals sine of x. If the x coordinate increases at a rate of 2 units per second, find the rate at which y changes over time when the point is at pi comma 0. So let's sort of visualize what's going on here. We have this sine curve, and you all know what the graph of the sine curve looks like. And you can imagine this point sort of traveling along the curve. And as it moves, its x coordinate changes and its y coordinate changes. And if it's moving from left to right, then its x coordinate is going to go to the right, which means it's going to get bigger. But the y coordinate could change. It could go up sometimes, it could go down sometimes. So the x and the y variables are changing over time. So what we want to do here is let's read our equation or our problem here carefully and label everything that we're being told in this problem. Right away it says that the x coordinate increases at a rate of 2 units per second. So if we have just a random point here with coordinates x comma y, then this x coordinate is increasing at a rate of 2 units per second is referring to a rate of change of x, and in calculus, rate of change is synonymous with derivative. So when it talks about how the x coordinate increases at a rate of 2 units per second, that means the derivative of the x coordinate is changing at 2 units per second. So how would we label that? Well, we're going to label it as dx over dt. Every derivative that we talk about in related rates problems is always with respect to time. And the units on this too can give you a clue here because we're talking about units on top, which are the x units, and then the bottom units are seconds, which are time units. So we know that this has to have a t in the bottom of our derivative because we have seconds in the bottom. So dx dt is this 2 units per second. Now what we're trying to find is the rate at which the y changes over time. Now rate means derivative, so how would we write or label the derivative of y? Well, we would just call that dy dt, and that's what we're trying to find, so that's going to be our unknown. And we want to know that when we are at the point pi comma 0. So once we have everything labeled in our problem, that's kind of step 1. Step 2 is going to be to come up with an equation that relates our variables. And our variables are this y and this x. How are these y's and x's related to each other? Well, remember, they're on this curve. So we are already told the relationship that has to exist between y and x. We're told that y equals sine of x. So that's the equation that we start with that relates our variables x and y. Now what we want to do is get derivatives involved because the information that we're given and the information we're trying to find are derivatives. So this is going to be our next step, step 3, to take the derivative of this equation implicitly with respect to time. So we're going to take the derivative with respect to time of the left side and the derivative with respect to time of the right side. Now, the derivative of y with respect to time. Remember, this t does not match this y. So we're going to take the derivative like we normally would. The derivative of y wants to be a 1, but by the chain rule, we have to multiply that by a dy over a dt. And because 1 times dy dt is just dy dt, usually we don't even bother writing that 1 in front. Now let's try that again on the right-hand side. What would be the derivative of sine of x with respect to t? Well, the derivative of sine of x wants to be a cosine of x, but because this t and this x do not match, we have to multiply this by a dx dt. Now, one common mistake that I sometimes see is students plugging in values too soon. So you want to get to this stage where you've taken your derivatives and sort of cleaned it up as much as you can first before you start plugging anything in. So now we're at that stage where we're ready to plug in whatever values we know. Now we're looking for dy dt, so I'm going to leave this side dy dt. But I do know what x is because we are on this point pi comma 0, which would be right here. And the x coordinate of that point is the pi. So I can substitute in now a pi for x. And then I also know what dx dt is. That's this 2. So we're going to plug in a 2 right there. Now remember your unit circle. What's cosine of pi? That's the same as 180 degrees. So that's a -1. And when I multiply that by 2, I'm going to get a -2. Now let's think about the units on this. What would be appropriate units for dy dt? Well, it should be the exact same units that we had for dx dt. So we're going to have units per second. You want to have those time units in the denominator. Now, does it make sense for this to be a negative answer? In this problem, it does, because if the point is at pi comma 0, what's happening to that y coordinate? It's going down as we travel along this curve. So that y coordinate is shrinking because we're getting closer and closer to that x-axis. So it makes sense for that y coordinate to be getting smaller when we're at the point pi comma 0. Okay? All right, let's try the next example. And this is a pretty typical, common example that you'll see in a lot of textbooks. Here we have air being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So let's draw a picture of this. We're talking about a spherical balloon. So here's my sphere, and in a sphere, a good dimension to know about is that radius. And think about what's happening. We're pumping air into this balloon. So as we add air, this balloon is going to grow. Therefore, its volume is going to get bigger, and its radius is going to increase as this balloon gets bigger and bigger and bigger. So that's sort of the situation. Now let's start labeling what we're told in this problem. Right here, this 100 cubic centimeters per second is supposed to be what the rate of change of the volume is. It's the volume increases at this rate. Now remember, rate in calculus means derivative. So this 100 cubic centimeters per second is some kind of a derivative. And if you're not sure from the words what it is, look at the units to help you have a clue. We have cubic centimeters on top and seconds on the bottom. So the bottom is time and the top is cubic units. Well, what do we measure in cubic units? We measure volumes in cubic units. So this is a volume over a time. So the derivative that this would represent should be dV over dt. And it's correct that this is positive 100 because as we pump air in, the volume should be growing. It should be getting bigger and bigger as the balloon grows. So that's our first derivative. The next thing it says is how fast is the radius of the balloon increasing. Now fast is a word that's asking about a speed or a rate. And again, speeds and rates are derivatives in calculus. So how would we label the derivative or the speed of the rate of change of the radius? Well, we would call that dr over dt, the rate of change of the radius over time. And that's what we're looking for. So that's going to be our unknown. And we want to know that when the diameter is 50 centimeters. So we have volume, we have a radius, and we have diameter. We need some kind of an equation that's going to relate all of these things. Now hopefully you recognize that radius and diameter are already related to each other. So there's a simple solution to kind of eliminate at least one of these variables. Instead of thinking of diameter as being 50 centimeters, we know that diameter is twice the radius. So if the diameter is 50, that's the same as saying the radius must be 25. So instead of thinking of diameter at all, let's just think in terms of radius. That way we only have a radius variable and a volume variable, and it just eliminates one of our variables, so the equation should be simpler. Now what is the equation that relates volume of a sphere to its radius? Now this is one that I would expect you to know. If you don't remember what it is, usually every textbook has these geometry formulas in the front or back cover. So you could just open up your textbook and look inside to remind you. But you'll probably see these kinds of problems a lot, so you'll get used to what this formula is. It turns out that the volume of a sphere is 4/3 pi r cubed. So that's the relationship that relates our radius to our volume. So now what we want to do, that we have this formula, is we need to get the derivatives involved. So what I'm going to do is take the derivative with respect to time of the left side and the derivative with respect to time of the right side. So we're doing this derivative implicitly with respect to time. Now the left side, dv over dt, the derivative of volume over time, that's just going to go to dv dt. Nothing special is happening over there on that left side. But on the right side, we need to use our power rule. We also have a constant multiplier out front. 4/3 pi is just a constant. So 4/3 pi is going to stay in our answer, and then the derivative of r cubed wants to be a 3r squared, but we're going to multiply that by our dr dt because of that chain rule. Now before I plug anything in, I'm just going to clean up things a little bit. These 3's are going to cancel out, so dv dt will become 4 pi r squared dr dt, and now I'm ready to plug in whatever I know. Well, I know dv dt is 100, so I'm going to put 100 on the left side. We knew, because our diameter was 50, that our radius was 25. So we're going to plug in 25 for this r, and it needs to get squared. And we're looking for dr dt. Don't plug in any of these numbers until after you have taken your derivative and cleaned it up. If you plug in too soon, then your derivatives are going to go to 0 because you'll just end up with a bunch of constants. So don't plug in until after your derivatives. Now let's clean this up. We have 100 on the left side. 25 times 4 would be 100, times another 25 would be 2500 pi. Don't bother getting a decimal for pi, just leave it in terms of pi. Now to finish solving this for dr dt, I can divide both sides by that 2500 pi. A couple of zeros will cancel out, and we get 1 over 25 pi, and that's what our dr dt is equal to. Now what kind of units should I have on this? This is a radius over a time, a dr over a dt. So you need units of radius, which were being measured in centimeters, over time. And the time that was being mentioned here was seconds. So dr dt is 1 over 25 pi centimeters per second, and it's positive because as the balloon grows, that radius is going to grow as well. Okay, the next example, a very typical one, the ladder problem. So here we have a 10-foot ladder rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So here having a picture is really key. Here's our wall, and then we have this ladder propped up against it. Now it's a 10-foot ladder, so right away the length of this ladder is fixed at 10 feet. That ladder is not going to change length. But what's happening is the bottom of the ladder, which is down here, slides away from the wall. So it's sliding this way at 1 foot per second. And that causes the top of the ladder up here to slide down the wall. And we want to know how fast it's sliding down the wall when the bottom of the ladder is 6 feet from the wall. So when this distance right here is 6. Okay? So we need to have some labels on things, and the first thing I want you to recognize is what pieces of this are changing. We do have a right triangle right here, and that's really important for us. But when we think about this right triangle, the lateral side, which is our hypotenuse, is that fixed length 10. But this horizontal side down here, this leg at the bottom, is going to be getting bigger as my ladder slides away from the wall. So this length right here changes. So we need to give it a variable name. So let's call this distance here x. Likewise, as the ladder moves away from the wall, the top of the ladder moves down. So this vertical distance changes as well. It's going to get smaller. So we need to call it a variable name. It's going to be called y. So we have a nice right triangle, and as you know, Pythagorean theorem applies to every right triangle. So that's what we're going to use to relate these variables. But before we get to that, let's label all the different rates and values that we know. So we already know that this hypotenuse is that 10 feet. We've already labeled that. Then it tells me that the bottom of the ladder slides away from the wall at a rate of 1 foot per second. So this is going this way at 1 foot per second, which means this distance x is growing at 1 foot per second. Now the rate at which it grows is its derivative, because that's a rate. So dx dt is this 1 foot per second. It's the rate of change of this horizontal distance. What we want to know is how fast, so that's a rate again, how fast the top of the ladder is sliding down the wall. So we want to know how much this vertical distance changes. And that's a rate as well. And since this vertical distance is being called y, then that rate of change would be dy over dt. And that's the one we are trying to find, so that's your unknown. And we want to know that when the bottom of the ladder is 6 feet from the wall. So when this distance here is 6 feet, and that distance is our x. So we want to know all of this when x is 6 feet. Okay? So that's all of the initial information that we're given. Usually in these problems, you're given one or most of the derivatives, and you're trying to find the other derivative that's unknown. Okay? Now we have all the information. Now we need that equation that's going to relate our variables. And I mentioned earlier that this is a nice right triangle, so the Pythagorean theorem will apply. So according to the Pythagorean theorem, the leg squared plus the leg squared equals the hypotenuse squared. So here's my equation. X squared plus y squared equals 10 squared. Now one common mistake is for students to plug in 6 right away, and that would be wrong because x is not always 6. It's only 6 at one moment in time. So you don't want to plug in that 6 until after you've taken your derivatives and you're looking at just the moment in time that you're interested in. So at this point, we're ready to go ahead and take our derivative with respect to t of the left side and the right side. And that right side just simplifies to 100. So the derivative of x squared, it wants to be a 2x, but because we're taking the derivative with respect to t, we need that chain rule, so we need a dx dt multiplied on the side. Plus, derivative of y squared wants to be a 2y, but we need a dy dt being multiplied. And over here, the 100 is a constant, so its derivative will always be 0. Now, at this point, you have some choices. If you wanted to, you could divide everything through by those coefficients of 2's to cancel out. So I could divide every term by 2, and that'll just make the 2's go away on the left side. And since 0 divided by 2 is still 0, the 2's gone completely. Now at this point, I'm going to just go ahead and plug in my information and solve for the one that I don't know. So we need to know what x is. Do we know what x is? Yes, that's that 6 feet that we were talking about earlier. We want to know when this is true, when x is 6 feet. So let's plug in 6 for x. Do we know dx dt? Yes, that was this 1 foot per second. So I'm going to plug in 1 for that. Do we know y? Well, I don't see y anywhere listed here. So let's leave that alone for a moment. Do we know dy dt? Well, that's the one we're trying to find. So I need to know y if I'm going to be able to solve this for dy dt, because that would otherwise give me 2 variables and I only can solve for 1. So how could we figure out what y is in order to be able to solve this? Well, you know the relationship between x and y at any moment in time. So if x is 6, what would that force y to be? We can use our Pythagorean theorem to figure out what y has to be at this moment in time. So if I plug in 6 for the x into my original equation, I'm going to get 36 plus y squared equals 100. So when I subtract 36 over to the other side, I get 64. And when I take the square root of both sides, I'm going to just take the positive answer, but that would force y to be 8. So this is a 6, 8, 10 right triangle. So this will be 8 feet when x is 6. So I can plug in 8 for this y. And now I have enough information to be able to solve for that dy dt that we were looking for. So this is going to be 6 plus 8 dy dt equals to 0. So I'm going to get 8 dy dt equals to negative 6. And if I divide both sides by 8, that tells me that dy dt is negative 6/8 reduces to 3/4. What are the units on this dy dt? Well, it should be the same units that I had for dx dt, and that was feet per second. So this will be feet per second. And then the last question I have is, why is it negative? Well, that should make sense, because as this distance grows, as I move the ladder off to the right, this top goes down, so my distance y shrinks. And that's why we're getting a negative rate of change, because that distance is getting smaller. So it makes sense that we got a negative. Okay? All right. The next example is the water tank problem, or the cone problem. And these are pretty infamous problems that you'll always see in every textbook, but these are probably the trickiest ones of them all. And drawing a picture here is really, really key. So here we have a water tank that has the shape of an inverted circular cone with a base radius of 2 meters and a height of 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. So first of all, let's draw our tank. Our tank is an inverted circular cone. So you want to kind of think of that as like an ice cream cone shape. It's a cone that's upside down. And the tank itself has a base radius of 2 meters. So that would be this dimension right here, and a height of 4 meters. So that's that height right there. Now we're pumping water into this tank. So at some moment in time, we have this much water in our tank. But as we pump in more water, that's going to rise and get taller and taller and taller. So what we're talking about here is water being pumped in at a rate of 2 meters cubed per minute. So look at those units. Meters cubed per minute. What do we measure in cubic units? We measure volume in cubic units. So 2 meters cubed per minute is a derivative because it's a volume per time. So this is dV dt. So 2 meters cubed per minute is how much the volume of this water, that blue stuff, is increasing as we keep pumping in water. So that's the first thing we know. What we're being asked to find is the rate, in other words, the derivative, at which the water level is rising when the water is 3 meters deep. Okay, so at some moment in time, this depth of this water is 3 meters at some moment in time. But that's constantly changing, right? As I keep adding water, that depth continues to grow and grow and grow. So I'm not going to actually want to label that 3. I'm going to actually want to label that a variable. I'm going to call it h. So here's my water, and that height, let's call it h, because that's changing over time. And at one moment in time, that height will be 3 meters deep. And what we want to know is when that height is 3 meters deep, what is the rate at which this water level is changing, is rising? So think about how you would label that. The rate at which the water level, our water level is this h, is rising. Well, what's the rate of change of this height? Well, we would label that dh dt. So we're looking for dh dt in this problem when, or at the moment in time, when that h is 3 meters. Okay? So what else do we have in terms of variables here? We have that h, that water depth. What is also an important dimension of this sort of small blue cone that I have? I've got this height, but there's also a radius that's important to know as well. Okay, so what we're going to do is we're going to relate the volume of our cone to the height and the radius. So what would be the volume of this small blue cone? Well, this is another one of those formulas that I kind of would expect you to know, but if you've forgotten, just look it up in your textbook in the front or back cover. The volume of a cone formula is 1/3 pi r squared times h. Okay? Now this one is a little bit tricky for us because if you look at the information that we were given in this problem, we were given information about dv dt. We want dh dt when we know h is 3. There's no mention whatsoever about a radius anywhere. So having this r in the problem is going to be troublesome because we're not given any information at all about what r is, let alone what its radius, or excuse me, what its derivative would be. So I don't know r and I don't know dr dt. So what we're going to do is we're going to try to eliminate the r altogether. And we're going to do that by finding some sort of relationship between this radius and this height. So some sort of formula that relates r and h. And that's going to come from a little bit of geometry. Because this great big cone has a radius of 2 and a height of 4, you can sort of visualize that as a big triangle like this. And then nested inside of that is our little black triangle, which is also a right triangle that has a radius r and a height h. These are similar triangles because they both have right angles and all 3 angles of these little right triangles are equal. And what we know from geometry is that similar triangles have sides that are proportional. So we can create a proportion out of these 2 similar triangles. So the big radius of the big triangle to the big height of the big triangle has to be in proportion to the small radius of the small triangle to the small height of the small triangle. So 2 to 4 has to equal r to h. And if you cross multiply, you get 2h equals 4r. And I want to solve this for r because I'm going to figure out what r is in terms of h. So if we divide by 4 and reduce, 2/4 is 1/2. So the radius is always 1/2 the height. And that relationship right there is what we're going to substitute in right here for this r to eliminate it. So here's what I mean. If I take this equation and I replace the r with 1/2 h, that's going to get squared and multiplied by h, but now you'll see that there's no more r variable at all. And since we didn't know what r was or knew any information about it, that's good news for us because now we only have v's and h's, and that's the information we were given in this problem. Now you definitely want to simplify this before we start taking our derivatives. So let's clean it up. We're going to get a 1/3 pi times a 1/4 h squared times h when we square both of these. And cleaning it up even more, 1/3 times 1/4 is 1/12. So this is going to be pi over 12, and an h squared times an h is an h cubed. So here's our new volume formula that has no radius involved anymore. So this is where you want to get to. You want to get to this volume so that it no longer has an r. Then you're going to take the derivative with respect to time of the left and the right side. We need to get those derivatives involved because that's the information we're looking for. So what's the derivative of volume with respect to t? Well, that's just dv dt. There's nothing really to do there on that left side. On the right side, the pi over 12 is a constant multiplier, so it stays put. And the derivative of h cubed wants to be a 3h squared, but we have to multiply that by dh dt. So we have dv dt equals 3 goes into 12 4 times, so this is pi over 4 h squared times dh dt, and now we're ready to plug in everything that we know. dv dt is 2 right here, so put a 2 on the left side. H is 3, and that needs to get squared. So we're going to have 2 equals 3 squared is 9, so this will become 9 pi over 4 times dh dt. And to solve for dh dt here, I could just multiply by the reciprocal on both sides. So I'm going to multiply by 4 over 9 pi on the right and 4 over 9 pi on the left. So these will cancel, giving me just a dh dt by itself. And 4 times 2 is 8, so this will be 8 on top and 9 pi on the bottom. And then finally, what about units? This is a word problem, so you always want to have proper units. Since this is dh dt, you want to have units of height on top, and our height was being measured in meters, and time on the bottom, and our time was being measured in minutes. So this is going to be 8 over 9 pi meters per minute, and it's positive, which it should be, because we're adding water into this tank, so it's going to continue to rise up and that height will continue to grow. So the cone problems are the toughest ones of all. The tricky part about them is that your initial volume formula has volume, radius, and height, and usually that is too many variables to start with. So what we do is we use similar triangles over here to get a relationship between our radius and our height, and we use that to substitute in so that we can reduce one of the variables and eliminate the radius altogether. After you clean that up, then you take the derivative with respect to time, plug in all your numbers, and solve for the derivative that you're looking for. Okay? All right. The last two problems, again, these are all the most common types of related rates problems that you will always see. All right? So the next one is the car problem. Here we have car A going west at 50 miles per hour, and car B is going north at 60 miles per hour. Both are headed for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? So drawing a picture here is really, really important, and you want to draw it correctly. Car A is going west. So here's car A. and car B is going north, and they're both heading towards the same intersection. So I'm going to want my two arrows to meet at the intersection where they're headed, and B is going north, so it would be going up towards that intersection. Car A is going 50 miles per hour. Car B is going 60 miles per hour. And we're talking about at what rate are the cars approaching each other. So if they're approaching each other, that means this distance between them should be shrinking so that they're getting closer and closer to each other. And we want to know what that rate is when car A is 0.3 miles from the intersection and car B is 0.4 miles from the intersection. Now this distance for A is not always 0.3. It's changing, right? Because car A is driving closer and closer to that intersection. So you need to use a variable for this distance right here. So let's call it little a. Similarly, this distance for B is getting smaller as well as B drives closer to the intersection. So because it's a changing length, you need to call it a variable name. Let's call it B. And the distance between the two cars is getting smaller as they get closer, so it needs a variable, so let's call it C. And since this is an intersection, that's a right angle. So what we have in these car problems typically is another right triangle. What makes this one different from our ladder problem is that the hypotenuse is not constant. In the ladder problem, that ladder was the hypotenuse and it was always 10 feet long. That's not the case here. You have 3 variables instead of just 2 in the ladder problem. Okay, so we're still going to use our Pythagorean theorem, a squared plus b squared equals c squared. That's going to be where we start, but before we jump into that, we need to label what all these other things represent. So let's start with this 50 miles per hour. That's the rate, or the derivative, of car A, and that's how fast this distance, little a, is changing. So 50 miles per hour is the derivative of that length a over time. Now, is this getting smaller or is this length getting bigger? It's getting smaller, right? Because car A is getting closer to that intersection. So technically, this 50 miles per hour is actually going to be a negative 50 because that distance is shrinking. So your derivative needs to be negative there since the distance is getting smaller. Similarly, 60 miles per hour is the distance for B changing over time, and it's also shrinking. So dB dt will be negative 60 miles per hour. And what we're trying to find is the rate, or derivative, at which the cars approaching each other are getting smaller and smaller. So the distance between the two cars is this c. So its rate of change is dc dt, and that's our unknown in this problem. And we want to know all of these things when this distance a is 0.3 miles, so little a needs to be 0.3, and when the distance b is 0.4 miles, so little b needs to be 0.4. So here's all the things we're told in the problem. Here's our equation that's relating all of those variables. Now we need to get some derivatives involved. So we're going to jump right in and take the derivative with respect to time of the left side and the right side. So derivative of a squared wants to be a 2a, but we have to multiply that by a dA dt. Derivative of b squared wants to be a 2b, but we're going to multiply that by a dB dt. And derivative of c squared is 2c times dc dt. Now just to make our life a little bit easier, every term here is divisible by 2. So let's go ahead and divide everything by 2. So we get a dA dt plus b dB dt equals c dc dt. And now we're ready to plug in. Do we know what A is? Yes, that's this 0.3. Do we know d/t? Yes, that's this negative 50 miles per hour. Do we know B? Yes, it's 0.4. Do we know dB/dt? Yes, that's negative 60. Do we know C? Well, it's not in my list here, but I need to know what it is because we're looking for dC/dt, and I won't be able to solve for that unless I know what C is. So how do we find C? Well, just like in the ladder problem, we're going to go back to our relationship. We know that no matter what moment in time we're looking at, the a squared plus the b squared always has to equal the c squared. So if that's true, then the moment in time when a is 0.3 and b is 0.4, that should tell us what the c has to be at that same moment in time. And you can use your calculator here to figure this out, or just realize that this is a 3, 4, 5 right triangle, and using the decimal in the right spot forces C to be 0.5 miles. So this C has to be 0.5 miles, so I can plug that in. Okay? And now we're ready to substitute in and figure out our values here. Okay, so if I pull up my calculator, I'm just going to type in 0.3 times negative 50 plus 0.4 times negative 60 and hit enter. So that left-hand side is going to be a negative 39, and then to finish solving for dC/dt, we would want to divide that by our 0.5, our C value. So if we divide that by 0.5, we're going to get negative 78. So we had negative 39 divided by that 0.5, and this gives us negative 78 for this dC/dt. What would be the appropriate units for this? Well, dC/dt is a distance over a time, so it's going to be the same units as our dA/dt and our dB/dt. So this is miles per hour, and it's correct that it's negative because these cars are getting closer and closer together, so this distance C should be shrinking. So they're getting closer and closer together at 78 miles per hour. Okay? All right, the last example is the shadow problem. All right, so in this one we have a person 6 feet tall is walking away from a street light 20 feet high at the rate of 7 feet per second. At what rate is the length of the person's shadow increasing? So definitely you want to draw a picture here. We have this 20-foot high street light. Okay, so this is 20 feet tall. And then we have a person who's 6 feet tall who's walking away from the street light. So he's going this way at a rate of 7 feet per second. And the light is shining down on this person so that their shadow is this length right here. So there's our shadow. So that's how you want to draw your picture. And again, we're going to assume that this is a right angle here and a right angle here. So this should look kind of similar to those triangles nested inside of each other that we had when we did our cone problem. It's going to be done very similarly in the fact that we're going to be using similar triangles to set up our equation. So here's what we have so far. Now let's label the things that we know. So the shadow is this horizontal distance in front of the person. So as he walks away at a rate of 7 feet per second, then that shadow length is going to change. So it needs to have a variable name. Let's call it S. And the distance between the person and the light is changing at that 7 feet per second. So this distance between the lamp and the person also changes over time. So let's call it X. and the rate at which he's walking away from that lamppost is that 7 feet per second. So that 7 feet per second is actually the rate of change of this distance x. Their distance between the two is growing at 7 feet per second. So that's the derivative dx over dt. And what we're looking to find is the rate at which the length of the person's shadow is increasing. Rate means derivative, so that means we're looking for the derivative of the shadow, and we're calling that s. So that means we're looking for ds over dt. Okay? We have the 6 feet already in there. We have our 20 feet already in there. We've labeled our 7 feet per second. So we've got everything labeled appropriately. What we need now is some kind of a relationship for an equation that's going to relate our x to our s. And the equation that we're going to use is going to come from a proportion that's relating our two triangles here. We have this small blue triangle right here in relation to our large red triangle. And these are similar triangles because all of the angles are equal. They both have right angles. These two angles in the upper corner are equal, and this corner angle is the same for both. So that makes them similar triangles, so their sides have to be in proportion. So you can set up this proportion in numerous ways. It's really your choice. I am going to do this side of the small triangle, which is my S length, compared to this vertical distance of my short triangle, which is the height of the man, which is 6 feet. So I'm doing this leg to this leg. So correspondingly, I want to do this whole leg in the big triangle, which would be the whole length of x plus the whole length of s, compared to this leg of the big triangle, which is the length of our street lamp, and that we know is 20. So we did leg to leg over leg to leg. Okay, so there's again variations of that. This is just the way I decided to set it up. Now to actually solve this and simplify it a little bit, you probably will want to simplify it first before you start taking derivatives. Otherwise it gets kind of messy with all these fractions. So what I'm going to do, since it's a proportion, is just cross multiply. So we're going to get 20 times s, or 20s, equals 6 times this whole numerator x plus x, which becomes 6x plus 6s. And that means we have some like terms. I've got a couple of s's here. So let's get them together by subtracting. So 14s equals 6x. If you wanted, you could even divide through by 2's to kind of reduce the numbers a little bit. That's up to you. But this is pretty simplified right now. So at this point, I would go ahead and take my derivative with respect to t of the left side and the right side. Now, we're taking the derivative of an s and an x, not a t, so you need to use that chain rule. The 14 is just a constant multiplier, so it will stay there, and the derivative of s with respect to t wants to be a 1, but we have to multiply that by a ds dt. On the right side, same thing. The 6 stays there. The derivative of x would normally go to 1, but we have to multiply that by a dx dt. So we get 14 ds dt equals 6 dx dt, and now we're ready to plug in. We know dx dt is 7, and we're looking for ds dt. So to solve for ds dt, I would just divide by 14. 7 goes into 14 twice, and 2 goes into 6 3 times. So that means ds dt is just going to be 3. And what would be appropriate units for this? Well, s is a length, so we want units of length over time. So it's going to be the same units that we had for dx dt. which were feet per second. And there's our answer. Okay, the last two examples that we're going to talk about are going to be related rates problems involving trigonometric functions. So this first one, we have a fishing line is being reeled in at a rate of 1 foot per second from a bridge 15 feet above the water. At what rate is the angle between the line and the water changing when 25 feet of line is out? So we definitely want to draw a picture here. We have this bridge, which is at a constant height of 15 feet. So this vertical distance here is always 15 feet. We don't need a variable for that because it's a constant amount. And then we have somebody on the edge of our bridge who's fishing, and they have their fishing line out at some distance in the water. Now he's reeling in that fishing line, so you can kind of visualize that at some point the line would be here, and then it would be here, and then it would be here, and so forth. So this distance is changing, and these angles down here between the fishing line and the water is changing, and the length of your fishing line is shrinking as well as he reels it in. So let's label our variables here. Since the fishing line is getting reeled in, it's getting shorter and shorter. So that's a variable. So let's just call it x. And the angle that they're talking about here is the angle between our fishing line, which is this red line, and the water, which is down here. So we're talking about this angle right here. Let's call that theta. So if it says that a fishing line is reeled in at a rate of 1 foot per second, 1 foot per second is a rate, which means it's a derivative. Which derivative is it? Well, it's talking about the length of this fishing line changing because we're reeling it in. So we're talking about this length here changing at 1 foot per second. And since we call that length x, then this would have to be the derivative of x with respect to time. Now, one more thing to note is the fact that this distance x is getting smaller as we reel it in. So this derivative technically needs to be a negative 1 foot per second to show that that distance is decreasing. Okay? Now we want to know at what rate or at what derivative is the angle changing. So our angle is theta, so its derivative would be d theta dt. So we're trying to find this d theta dt, and we want to know this when 25 feet of line is out. So we want to know this when this x is 25, because that's our fishing line. So there's everything that we have. Now we need to figure out some kind of equation that's going to relate our x and our theta. Now in order to figure that out, look at what we have over here. This is a right angle, so we have a right triangle where we know this side is always 15, the hypotenuse is x, and this angle is theta. Now in relation to that angle theta, we know the opposite side, and we want to know about the hypotenuse side. So which trigonometric function relates the opposite to the hypotenuse? Well, that's your sine curve. That's your sine function. Sine of theta is opposite over hypotenuse. So in our diagram, the opposite side was 15, and the hypotenuse would be that x. So the equation that we want to work with is sine of theta equals 15 divided by x. So now that we have our equation relating the variables, now we want to take derivatives to relate the derivatives. We're going to take the derivative with respect to t of both sides. So the derivative of the sine theta and the derivative of the 15 over x. Now just planning ahead here a little bit, we know that we're going to want to take the derivative of 15 over x. It's probably easier to do that if we move that x up to the top and make it a -1 exponent. So let's go ahead and take these derivatives. The derivative of sine of theta wants to be cosine of theta, but because we're taking the derivative with respect to t, we need to multiply this by d theta dt. On the other side, the derivative of 15x to the negative 1 wants to be negative 15x to the negative 2, but we have to multiply that by our dx dt. Now let's clean it up just a tad. I'm going to take that x to the negative 2 and push it back down in the denominator. So negative 15 over x squared times that dx dt. And now we're ready to start plugging in what we know. Well, we know what dx dt is. Dx dt is negative 1. We know what x is. X is 25. So this will be negative 15 over 25 squared. We're looking for d theta dt, so we need to know what either theta is or cosine of theta is in order to figure out this piece right here. Now, I don't know what theta is. They don't tell me that in the problem, so chances are there must be some way to figure out either what theta is or what cosine of theta is. And it's going to go back to this triangle to help us figure it out, because we want to know what this theta or cosine theta is at the exact moment when x is 25. So if this hypotenuse is 25, how could we figure out what cosine of theta would need to be? Well, cosine of theta is the adjacent side over the hypotenuse side. We know what the hypotenuse is. That's 25. What we don't know is this adjacent side. So let's call it y. And in order to figure out what that adjacent side is, we could just use Pythagorean theorem on this right triangle. So 15 squared plus y squared needs to equal 25 squared. 15 squared is 225. 25 squared is 625. So when I subtract that 225 over, 625 minus 225 is 400, which means y is 20. So at the moment in time that we're looking at, the adjacent side will be 20. Now notice here that you could solve for theta by taking an inverse cosine or doing something like that, but it's not even necessary because we don't want to know just what theta is. We want to know what cosine of theta is. So what I'm going to do is I'm going to replace this cosine of theta with 20 over 25. I'm just going to use that whole fraction, and that way we don't even have to bother figuring out what theta happens to be. So all we have to do now is finish solving this. So we have 20 over 25 times d theta dt equals positive 15 over 625. And to finish solving, I'm going to multiply by the reciprocal of my left-hand fraction. So I'm going to multiply by 25 over 20. We know that 25 goes into 625 25 times. We can cancel out some 5s here. I'm going to be left with a 3 here and a 5 here. So it looks like we're going to end up with d theta dt being 3 on top, and 5 times 20 is 100. What kind of units should be on this? Well, we want units of theta over units of time. And in calculus, whenever you're taking derivatives of any kind of trig functions, you always want to be in radians, not in degrees. So since I was using derivatives of trig functions here, I'm going to let my theta be units of radians, and my units of time, those were seconds. So my units that I should have should be 3/100ths radian per second. And that's a positive answer, because as these fishing lines get pulled in, that angle theta is getting bigger and bigger and bigger until it almost gets vertical from that last pull in. Okay? All right, let's try one last example here. We have a patrol car is parked 50 feet from a long warehouse. The revolving light on top of the car turns at a rate of 30 revolutions per minute. How fast is the light beam moving along the wall when the angle between the perpendicular line from the patrol light to the wall and the line from the patrol light to where the beam meets the wall is 30 degrees. So this one is a particularly tricky one to kind of visualize what's going on. So here's how I'm going to imagine it. We have our light right here. Okay, the light's shining out. And then we have our warehouse wall over here. And you want to visualize this light. Let me make it yellow just so that we can see what it is. This light, imagine that it's spinning clockwise around in a circle. So eventually that light is going to hit the wall over here and then sweep along this wall as it goes around counterclockwise. The perpendicular distance from the light to the wall would be this right here, and we're told that because the patrol car is parked 50 feet from this warehouse, then the distance from that light to the warehouse should be this 50 feet. Now this angle that we're talking about is the angle between this perpendicular line and where the line meets, or where the beam meets the wall, which is this red line over here. So the angle that we're talking about is this angle theta. And this light is shining along this light and moving along this wall. So we have this light sort of sweeping across, and as it's moving, this distance from the edge of the wall on over is growing. So let's call this distance right here x. Okay? So now we have some things labeled. Let's go ahead and figure out what some of these numbers represent. We already know that 50 is this distance, perpendicular distance from the light to the wall. And then it tells us that the revolving light on top turns at a rate of 30 revolutions per minute. Now that's how fast this light is spinning around. So that's how fast this angle theta is rotating around. So this is our d theta dt right here. The problem is, look at the units on this. This is revolutions per minute. And we can kind of imagine that to solve this problem, we're probably going to need to use some trigonometry to get an angle involved. And when we do trigonometry in calculus, we want to be in radians, and we don't want to be in revolutions or degrees. So it's not a good idea to leave our answer in these particular units. So I'm just going to do a little conversion. I know that if I convert revolutions to radians, I would need my revolutions to be on the bottom here and radians on the top. I know that in one revolution, that sweeps through 2 pi radians. So multiplying across, 30 times 2 pi gives me 60 pi radians per minute. So all I did there was change my d theta dt so that it was in terms of radians instead of revolutions, just to make it more consistent with what we do in calculus. Okay, what do we want to know? We want to know how fast this light beam is moving along the wall. Well, that's what this x represents, this distance x as the light beam moves along the wall. So we want to know how fast this x is changing. So we're looking for the derivative of x with respect to t. So that's our unknown. And we want to know this when this angle theta is 30 degrees. Now, 30 degrees, that's in degree mode. If you prefer, 30 degrees is pi over 6 radians. And that way we're consistently always using radians. Okay, we have everything labeled. Let's go ahead and come up with some kind of an equation that represents this triangle. We have our theta down here in the corner, so in relation to that, the x would be the opposite side, and the 50 would be the adjacent side. So which trigonometric function relates opposites and adjacents? Well, that's tangent. So tangent of theta is opposite over adjacent, which in our problem, the opposite side was the x, and the adjacent side was the 50. So tangent of theta equals x over 50. if you want, you don't have to do this, but if you don't want to deal with fractions, you could go ahead and multiply that 50 across to the other side and make this become 50 tangent of theta equals to x. That's just a choice that's up to you. Now at this point, we're ready to get our derivatives involved. So I'm going to take the derivative with respect to t of the left side and the derivative with respect to t of the right side. Now that 50 will just stay there because it's a constant multiplier. The derivative of tangent is secant squared, so the derivative of tangent theta will be secant squared theta, and the derivative of the theta becomes d theta dt. And then on the right side, the derivative of x would normally just go to 1, but we would have to multiply that by a dx dt. So we're ready to start plugging in. We're trying to solve for dx dt, so I'm going to leave that as is. We know that d theta dt is that 60 pi, and we need to know what secant squared of theta is, and in this problem, unlike the last one, we're actually told what theta is. Theta is pi over 6. So we're going to go ahead and substitute in pi over 6 for that theta. Now we're going to have to do a little bit of evaluating here. We want to know what secant of pi over 6 is. Well, that's 1 over cosine of pi over 6. And that's 30 degrees on your unit circle. So cosine is the x-coordinate, and the x-coordinate of our terminal point for pi over 6 is root 3 over 2. So 1 over that flips it to 2 over root 3. Now we didn't just want secant, we wanted secant squared. So let's go ahead and square this 2 over root 3, so it's going to become a 4/3. So all of this becomes 4/3. So we need 50 times 4/3 times 60 pi. So 3 goes into 60 20 times. 20 times 4 is 80. 80 times 50 is 4,000 pi. And that is what our dx dt equals. Let's get some units on it. We need units of x. X is a distance, and our distances were measured in feet. So we want feet on top, and our times were being measured in minutes. So this is going to be 4,000 pi feet per minute for our final answer. All right, that concludes our lecture on related rates. If you're having any trouble with the homework problems, make sure that you look back at these 8 problems. These are all pretty typical of what the homework should be like. Good luck.